Welcome back to another explainer. Today, we're unlocking the absolute secrets of the quadratic graph. You know, it's the mathematical hero behind the arc of a thrown basketball, the curve of a suspension bridge, you name it. We're going to map its shape, predict exactly how it moves, and of course, help you totally master it for your exams. So, let's just jump right in.
Okay, so here's our roadmap for today. First, we'll meet the parabola. Second, we'll look at transforming the graph. Third, we've got a 5-step sketching recipe. Fourth, parabolas and intersecting lines. And finally, number 5, avoiding those common exam traps.
All right, section 1, meet the parabola, the anatomy of a quadratic graph.
So, a quadratic graph, which is commonly known as a parabola, is basically this U-shaped curve defined by the general equation y equals ax squared plus bx plus c. Now that x squared part, that is absolutely non-negotiable. That's literally what gives the graph its signature beautifully symmetrical U-shape. So whether the curve is wide, narrow, high up, or way down low, as long as the highest power of x is a 2, you are definitely looking at a parabola.
Just like human anatomy, a parabola has specific, recognizable features that dictate exactly how it behaves. First up, we've got the vertex, or the turning point. Think of this as the absolute peak of the mountain, or the lowest point of the valley on our graph. Next is the axis of symmetry. Because parabolas are perfectly symmetrical, you can draw a perfectly straight vertical line right through that vertex, and the left side will be an exact mirror image of the right. Then we have our intercepts. The x-intercepts, which are often called the roots, are where the graph actually touches or crosses the horizontal floor. That's where y equals 0. And finally, the y-intercept. That's where our curve crashes into the vertical y-axis, which happens anytime x equals 0.
Now you might be wondering, how do we actually know if our U-shape is facing up or down? Well, it all comes down to the leading coefficient. That number attached to the x squared. If it's positive, like y equals x squared, the graph opens upward. It looks like a big smile. And because it's a smile, the bottom of that curve forms a minimum point. But what if we throw a negative sign in front, like y equals negative x squared? Well, our parabola flips. The smile literally turns into a frown, opening downward, which means our vertex is now a maximum point, right at the very top.
Moving on to section 2, transforming the graph, giving the parabola superpowers.
Okay, I want you to treat this slide as your ultimate cheat sheet. Seriously, by making just tiny algebraic tweaks to our equation, we can physically move and mold the graph. Adding a number at the end, like a +4, well, that acts like an elevator, shifting the whole graph straight up. Subtracting? That drops it down. But look closely at the horizontal shifts. These are the ones happening inside the parentheses. And this is vital. Whatever is inside the brackets actually does the exact opposite of what you'd expect. A -2 moves the graph to the right, and a +5 shifts it to the left. Wild, right? We can also stretch the graph to make it narrower by multiplying by a whole number, or compress it to make it wider using a fraction. And, as we just learned, multiplying the whole thing by a negative acts like a mirror, reflecting it completely upside down.
All right, let's get practical. Section 3, sketching in 5 steps. The DIY sketch recipe.
Let's actually sketch out the equation y equals x minus 1 squared minus 4. Step 1, we got to grab the vertex. Based on those transformations we just talked about, the -1 inside shifts us right by 1, and the -4 drops us down 4. So our vertex is sitting right at 1, -4. Step 2 is basically a freebie. The axis of symmetry is just the x value of that vertex, so x equals 1. For step 3, we need the roots, the x-intercepts. So we set y to 0 and solve the equation. If we move the 4 over and take the square root, we'll find it hits the x-axis at 3 and -1. Step 4, we find the y-intercept by just plugging a 0 in for x, which gives us -3. Finally, step 5, you just plot those 4 specific points, the vertex, the 2 x-intercepts, and the y-intercept, and connect them all with a nice, smooth U-shape. And boom, you've just sketched a perfect parabola, and you didn't even need a calculator.
Next up, section 4, parabolas and intersecting lines, a collision course.
I want you to just think about this for a second. If you draw a big U-shape on a piece of paper, and then you take a ruler and draw a completely straight line across that exact same paper, how many different ways can they actually interact?
Well, there are actually 3 distinct visual outcomes when these graphs share the same space. First, the straight line might slice right through the U-shape, cutting across it and creating exactly 2 points of intersection. That means 2 mathematical solutions. Second, the line might just graze the very edge of the parabola, maybe right at the vertex or somewhere along the side. We call this a tangent, and it gives us exactly one point of intersection. Finally, the straight line could just completely miss the parabola altogether, passing underneath it or way above it, and that means there are 0 points of intersection and absolutely no real mathematical solutions.
Now, visualizing the collision is great, but we also need to be able to solve for the exact coordinates of the crash using math. Let's say our parabola is y equals x squared, and our straight line is y equals x plus 2. Step 1, because they both equal y, we literally just smash them together. We write x squared equals x plus 2. Step 2, we rearrange everything over to one side to set it all to 0, giving us x squared minus x minus 2 equals 0. And now we're back in familiar territory. Step 3, we factorize that quadratic equation to get our x values, which end up being 2 and negative 1. But wait, remember, a coordinate is an x and a y. So for step 4, we take those x values and plug them right back into either of the original equations. Doing that reveals our exact collision coordinates, 2, 4, and negative 1, 1.
Almost there. Section 5, Avoiding Common Exam Traps, Your Survival Guide.
Okay, so the absolute crucial thing here is watching out for these sneaky little traps. Like we covered earlier, the biggest mistake students make for sure is with those horizontal shifts. When you see x plus 3 inside the parentheses, your brain instantly screams, move right. But no, it's totally counterintuitive. It actually moves left 3 units. Another massive trap is trying to find roots without first explicitly setting y to 0. Seriously, do not skip that step. Also, please don't just blindly draw a smile on your graph. Always check if that leading coefficient is negative, because that flips it right into a frown. And finally, pay super close attention to your operators. Multiplying by 2 stretches the graph, while adding 2 just simply translates or slides the whole thing up.
To make sure you walk away fully equipped, I want you to take a mental picture of these essential tips. This is your ultimate game plan. Whenever you're faced with a quadratic graph, always hunt down the vertex first. It basically anchors everything else. Also, use the axis of symmetry to your advantage. If you find a point on the right side, you get the mirrored point on the left completely for free. Always double-check your up or down orientation. When dealing with lines intersecting, equate those equations immediately. And please, for the love of math, clearly label your coordinates and intercepts on your exam paper so you actually lock in full credit.
I'm going to leave you with one golden rule. Always identify the vertex first. It's the beating heart of your parabola. It's the starting line for your sketch, and it is absolutely the key to unlocking these equations. Master the vertex, and you literally master the curve. Thank you so much for joining me on this explainer. It's been a blast. So what kind of mathematical curve are you going to conquer next? Keep exploring, keep graphing, and I'll catch you next time.